Hello, welcome to our lesson on graphical differentiation. So graphical differentiation is exactly that. It's differentiating, which means we're finding a derivative based on a graph. Because it just so happens that there are a lot of cases where we don't have an equation for a function, but we need to be able to find its derivative. And we're going to see more applications of this later. But again, there are times where we don't have an equation, so we can't find a derivative that way. If all we have is a graph for a scenario, and that graph can't be illustrated by some equation, the only way to find its derivative is by actually analyzing the graph, the slopes of the graph to be specific. So if we're going to find a derivative and all we have is the graph, then we are applying this process that we call graphical differentiation. The only way to do it is to analyze, or by analyzing the graph, specifically the slope, because when we're finding the derivative, remember the derivative is the instantaneous rate of change at any point along the curve, so we just need to identify the slope of each point on our original function and then use those slopes to create a graph of our derivative. Now, this process is a little tricky. Sometimes it's one of these things that you'll just get it right away, and sometimes it takes a little bit, and sometimes, I don't know, you just can't ever wrap your brain around it because it's a very visual concept. I want to just warn you that this isn't going to be a focal point of what we do for the rest of the course, so just try to pick up the basics of it, and if it makes perfect sense, awesome. If you can just get a little bit of it, you're going to be fine. Again, this isn't a focal point for us. It's just to sort of reinforce some of the concepts, okay? So let's take a look. Here we have a graph of a function, and based on the graph of this function, we want to try to make a graph of its derivative. So again, in order to do this, graphical differentiation, we need to analyze the slope of this graph that we're given. So what is going on with the slopes at each of these intervals, or at each of these points, or however we want to look at it. So I made a little table here to try to organize the work, where again we want to focus on x values for our function, and at those x values, at those frames of reference, whether it's a specific location or an interval, what is happening for its derivative, which means what is happening with its slope. Okay? So if I'm looking at this graph, first of all, everything that's happening over this particular interval is exactly the same. Now this particular interval of x values would be all of the x values that are less than -2. So I'm going to start in my table by writing down what is happening for my x values that are less than -2, what is happening to the slope, because that's what's happening to my derivative. Now since that's linear, my slope is going to be constant. So over this interval, again of x's less than -2, this is the place I'm looking here, the slope is a constant, up 1 over 1, up 1 over 1. From one point to the next, if I rise 1 and run 1, my slope is a constant positive 1. So for all the x's that are less than -2, my slope is positive 1, which means my derivative will be a positive 1 for all the x values less than -2. Okay? Now if I look at the next there's another interval here where exactly the same thing is happening over that entire interval. So over this interval here, from x equals -2 to x equals 0, I have again a constant slope, but it is decreasing here, which means my slope will be negative, versus in this first one, I had an increasing portion of the graph, and that increasing portion of the graph meant that my slope had to be a positive, right? So positive means our slope will be or increasing means our slope will be positive, decreasing means our slope will be negative. And just so we're careful with the words, increasing and positive does not mean the same thing. Increasing means we're going up from left to right. Positive means we're above the x-axis. So if this graph is increasing, my slope will be above the x-axis. That's where positive 1 is. Okay? So just to make sure we're good on vocab. Now, the next interval I'm looking at here, again, between -2 and 0, put this down here, between sorry, that's my highlighter, between -2 and 0, we have a constant slope here, and in this case, decreasing, we have to go down 1 and right 1 to get to the next point, so down 1, right 1, or down 1, right 1. I drew that on the other side of the line, but that's a slope of -1. So my slope's going to be a -1. Now I skipped a box here because at this point we have a sharp corner. And if you remember from our definitions, we talked about if we have a sharp corner on a graph, then our limit is not going to exist, and our limit has to exist in order for our function to be differentiable. And so there's no derivative at a sharp corner. Our slope would be undefined there. So in my table, I'm going to make a note that at x equals -2, our slope is undefined. Those sharp corners are no good. All right, so we're making our way, okay? Now, again, I have a discontinuity in my function here at x equals 0. So at x equals 0, that discontinuity means our limit's not going to exist, which means we're not differentiable. So we're going to say also at x equals 0, our slope of our tangent line is going to be undefined. So our derivative will be undefined. So we're going to have some holes or something of that nature in our derivative function, but let's get there in a second. Now, after that discontinuity, that second spot where we're undefined, what's happening to this section of graph? Now, this section of graph, this would be for all the x values that are greater than 0. That section is increasing, which means my slope should be positive, but it's not increasing at the same rate. Like this one is a constant, it's the same all the way through, and this one is a constant, it's the same all the way through. That's not the case for this piece. So we need to examine a little further what's happening with the slopes at each of these points, or at least some of them, to get the idea of what's happening. So let's get as close as we can to 0 and try to approximate a slope. Like, let's say we wanted to look at x equals a positive 0.5. So if we're at 0.5, this is the spot we're looking at here. If I drew in my tangent line, it's just a sketch to try to approximate what's happening, my tangent line might look something like this. My slope looks to be, I don't know, pretty close to rising 2 and running 2, pretty close to a 1 there. So let's say that this slope at 0.5 is about a positive 1, and a positive makes sense because this thing is increasing. Now if I go before 0.5, so if I'm like here, maybe I can't approximate this, but I know it's going to be bigger than where I was before. And so if we go this way, the slope is going to be increasing. But what happens if we go the other way? So here, let's say I go to x equals positive 1. So at positive 1, what's going on with my slope? Looks like I can rise 1 and run 2-ish to get to another point. So it looks like my slope is going to be about a half. And let me go ahead and move over now to maybe x equals 2. If I go over here to x equals 2, let's see, try to draw in something that looks like a tangent line and try to again approximate a slope. Looks like I'm rising 1 and running 4. So it looks like at 2 I'm going to be at about 1/4. And what's going to happen if I continue is that slope is going to continue to decrease, because you can see that this graph is getting flatter and flatter and flatter. So as we're flattening out, my slope is going to get closer and closer to 0. But because it will continue increasing, it will not flatten out completely. So it's going to approach 0. So as we continue moving this way, I'll just make a note for myself. This is going to continue to decrease, and approaching, it's going to continue to decrease, and it's going to approach 0. So approaches 0. It will flatten out, but never flatten out completely, because this piece of graph will keep going up. All right, so let's try to make a graph of our, oh, I gotta sneeze, I'm so sorry. Let's try to make a graph for our derivative, okay? So we said for all the x values that are less than -2, all this area over here, our slope was a constant positive 1. So when I make this graph, that means when I go to anything less than -2, like at -3, I'd be a positive 1. At -4, my slope was a positive 1. At -5, my slope was a positive 1.
all of these x values less than -2, not equal -2, because at -2 we said we're undefined, so I'm going to put an open circle there. But for as close as we can get to -2 and everything less than that, we had that constant slope. So if we have a linear piece of graph like we see here, we should have a constant slope, which means a flat piece of graph for our derivative. Okay? Now at -2 we were undefined, so I made an open circle there, but as close as we can get to -2, our slope was a constant 1. And then between -2 and 0, the same thing was happening. We had a constant slope here, so we should have a constant piece of graph for our derivative. But over that interval, it was -1. So remember, at -2 we were undefined, but as close as we could get to that here, we're at -1. So anything in between -2 and 0, this little section of graph, and actually both of those endpoints are undefined, that section in there had a constant slope of -1. So all those outputs for the derivative would be -1. But at 0 and at -2 and at 0, those were both places we were undefined, so I'm going to cap that little section off with those open points. Okay? And now the last little piece. So at 0.5, we said that our slope was going to be a +1. And then at 1, we said it would be a half. And then at 2, we said it would be a fourth. And then what would happen is that this was going to keep decreasing and approach 0. So it's going to kind of move this way. And then in between a half and 0, like I know this graph is not going to get to 0. Oops, sorry. Not going to get to 0 because we're undefined there. But I really need to know what's happening in between this little space. So does the slope increase or decrease? Now, it should make sense again what's happening, but let me just go back here. So at 0.5, we figured out our slope. And then if we're here, our slope would be steeper, so it should be bigger. And that would be the continuing trend as we move downward. We get really closer and closer to a vertical line. Now, a vertical slope would be undefined, right? A vertical line has an undefined slope. But that's going to get closer and closer to vertical, which means it gets bigger and bigger and bigger because it gets steeper and steeper and steeper. So on this side of our graph, we would just continue increasing, but we're not going to be able to get to 0, that the graph was undefined there at 0. And that looks really bad, but let me just try to sketch this in a little cleaner. So something like this, okay? So that's the concept. The important takeaways from this particular example would be, again, at sharp corners, it's like a sharp corner here, or at discontinuities like we have here, places where a limit wouldn't exist. Remember our instantaneous rate of change based on the definition of the limit. Anytime we have those discontinuities or places where the limit doesn't exist, our instantaneous rate of change is not going to be possible to find. So our slope is undefined at those places. Okay? So those undefined places means we have holes or asymptotes or discontinuities in our derivative function. Also, if we are increasing, then we should have a positive slope. If we are decreasing, we should have a negative slope. So an increasing interval, again, a positive slope means that piece of our derivative function should be above the x-axis. Negative slope, decreasing function means our slope would be negative or below the x-axis. Okay? So hopefully those takeaways are making sense. Let's try it again. And sometimes, again, this is just tricky, but we do our best, and if some of the concepts make sense, then I'm pretty happy with that. So let's look here. Here's another function. If I'm looking at this interval of x values less than -1, again, the same behavior here, so we can categorize this in one shot here. Let's say, what's happening for all the x's that are less than -1? Well, the slope here, or this being constant, means our slope is 0, right? I'm not rising at all to get from one point to the next. So all along that interval, our slope, which is what's happening for our derivative, is going to be 0. Okay, so let me go ahead and piece this out. All my x's that are less than -1, like at -2, my slope is 0, so my output would be 0. Output would be 0. Output would be 0. All of these values were going to be 0. But when I get to -1, I have that sharp corner. It's going to be undefined. So at x equals -1, our slope is undefined. Okay, so if I'm making the graph over here, again, at -1, we're going to be undefined, so I'll put an open circle there, but as close as I can get to -1, all the slopes leading up to that are 0. So I have a constant 0, right? A constant set of x-intercepts on that section of my derivatives graph. Okay, now what's happening in the next portion? So we turn the corner here, and I see that this graph is going to be increasing until we get here. So I want to now examine what's happening over that interval from -1 to +1. Now we're increasing, so that means the section of my derivative graph should be positive. That means it's going to be above the x-axis. But at what rate are we increasing? I need to get a couple of points here, so I need to actually figure out some slopes. Now, I know at -1 I'm undefined, so I want to try to get as close to -1 as possible. So I'm going to say really close to -1 what's happening. So like if I'm here, for instance, and I drew in a tangent line, then I don't know, approximately what's my slope going to be? It looks like I could probably say it's close to a +3. So let's just say as close as we can get to -1, we're going to be at about a +3. Okay? And then if I move over to, let's say, 0. So let's say I go here to an x value of 0 and drew in another tangent line here. Then what's my slope going to be? Looks to be pretty close to maybe 2-ish. So I'm just going to say my slope there is going to be like about 2. And then if I go to 1, what's happening? Well, if I draw a tangent in there at that turning point, my slope is actually going to be a horizontal line, which means my slope is going to be 0. So at x equals 1, I have a slope of 0. And that's another kind of a big takeaway here. If we have a turning point in a graph like we have here where we change from increasing to decreasing or vice versa, we will have a horizontal tangent line. So at turning points, our slope is going to be 0. So if our slope is 0, that means our derivative is 0. That means our derivative should be touching the x-axis, just like it was touching the x-axis here where all of our slopes were 0. Okay? So that means we have an x-intercept on our derivative function anytime our slope is 0 or anytime we have a turning point. So that connects directly to an x-intercept for f prime of x. Kind of, again, a big takeaway there. All right, so let's try to sketch out what's happening here. As close as we could get to -1. So pretty close to -1. We said our graph would be up here at 3 because our slope would be 3. Now, I'm going to, again, start this with an open circle because we're not defined at -1. But just after that, we'd be up here at 3. And then we're going to go down to 2. And then we're going to jump down here. I don't know if that's 2, 1.5, jump down here to 0. And this is going to be just continuing to decrease as we went this way. So I'm just going to make this section decrease here. And then if we look at the other side, so this area here, -1 to 1, that was this area here. If I go to this little piece, this is going to be moving at the same rate as the other side, like there's some symmetry and it looks like a little parabolic piece of this graph. So if at 0 our slope was 2, at 2, where am I looking? At 0 if we have a slope of 2, then at 2 we should have about the same slope. Now I know at 2 it's going to be undefined again. So I'm going to say at x equals 2 our slope is undefined because we have that sharp corner in the graph. But if we could get really close, so really close to 2, again our slope there at 2 would be the same as at 0, which would be about 2 again, or 1.5, or I don't know, I'm just kind of estimating what that's going to be. Okay, so what's happening here at 0 and here at 2 is approximately the same behavior, just one's a positive slope and one's a negative slope, which means one piece of it is above the x-axis and the other piece of it is below the x-axis. So here at 2 we're going to go down here and make this same, this is, I don't know, maybe should be kind of linear in here, but we're just trying to sketch this out. But we want to end this with an open circle again because at 2 we're undefined. All right, and then the last piece of this is not so bad because at the end of this we have change colors here, for all the x values that are bigger than 2, so we have this portion of graph which has a constant slope, so we should have a constant piece of our derivative function. So for all the x's that are greater than 2, what's our slope? Well, it looks like I would go down 1 and right 3 to get to that next point. So we're going to say our slope would be a negative 1/3. So a negative 1/3 would be like, I don't know, around here-ish. So I want to start with that open circle because we're not defined, but then we're going to be a constant slope of 1/3 all the rest of the way here for all those x's that are bigger than positive 2. So the graph of our derivative would look something like that. Now when you get to your assignment, don't freak out, you're not going to have to draw these, it would be really tough, but you do need to make some decisions on what's happening given the graph to its derivative. So again, some of the key takeaways that I want you to get from this. If your function is linear, so if f of x, the function that's given to you, is linear, that means it has a constant slope, which means the derivative function should be constant. It means it should be flat. So if your function is linear, its derivative is constant or flat. Also, if your function is discontinuous, if it has a sharp corner, if it has a vertical tangent line, any things that would cause the limit not to exist would means the slope is going to be undefined, the instantaneous rate of change is undefined. So any places like that, your derivative is undefined, so it would be a hole or an asymptote or some kind of discontinuity in that graph. If your original function is increasing, and increasing means a positive slope, so that means your derivative function would be positive. Now be careful, positive is location based. If f of x is increasing, the derivative being positive means it would be above the x-axis. Okay, and similarly, if it's decreasing, decreasing means a negative slope. A negative slope means we would be negative outputs, that would be a negative y's below the x-axis. So decreasing is telling you your derivative should be below the x-axis. And then another big takeaway is one we saw in the previous example. If f of x is constant, so if your original function is constant, that has a slope of 0, or it has a horizontal tangent line, again a slope of 0, then your derivative function would be equal to 0, because your slope is 0, which means it should be intercepting the x-axis. So if your original function is constant or has a horizontal tangent line, if you have a slope of 0 on your original function, then your derivative should be intercepting the x-axis. Okay, so those are the big takeaways. Now let's try to use those for just 2 more examples, where you're given a graph, you're given its derivative, and you're trying to figure out which one is which. Oh my gosh, I'm so sorry. The sneeze finally happened. Okay, so you have a function, you have its derivative, you have to figure out which is which based on some of those highlights that we talked about just a second ago. So we have these 2 graphs. Let's, I don't know, just pick one and say, okay, what if this one is our original function? So I'm going to go with this red one here, this linear piece. Let's say that this is the graph of our function. If that's the case, if this is f of x, the original function, that means f of x would be linear, then the derivative function, f prime of x, should be constant. Now, if that is our, again, if that's our original function, if it's linear, it's got a constant slope, the derivative function should be constant, the derivative function should be flat. But if you look at the other graph that's in the picture, it's definitely not flat, it's definitely a parabola, which means this linear piece cannot be the original function. So since this is not possible, then the blue one cannot be our original function. So just based on that, I know that this is going to be our derivative because it can't be the original function. And actually, let me change colors. I know that this is going to be our derivative because it can't be the original function. That means this is going to be our original function. Okay, now just so you can see again some of the highlights we talked about, we said wherever our function has a horizontal tangent line, has a zero slope, our derivative function should touch the x-axis. So at turning points, that's going to happen. So here, for example, we have, let me change colors again. Here, for example, we have a turning point. We have a horizontal slope. So here, we see our derivative function touch the x-axis. We also said if our function is decreasing, which that's what's happening over that first part of the parabola, then the graph of the derivative should be negative, which means it should be below the x-axis, which is what's happening here. So this piece was decreasing, which means this corresponding piece, that same domain, should be negative, below the x-axis. And then we also said if our original function was increasing, which is what's happening here, then the slope would be positive. So the derivative should be positive or above the x-axis. So this piece that's increasing corresponds with this piece, which is positive. Again, meaning above the x-axis. And again, negative meaning below the x-axis. So hopefully this all makes sense. Now, just to point out something else that's going to be helpful for us moving forward. Hopefully you recognize f of x as a quadratic function, right? That parabola is produced when our equation has an x squared in it, and its derivative is a linear function. That is always going to be the case. When we are finding the derivative of a quadratic function, it will always be a linear function. And we're going to talk more about that later, but I think it's worth noting the derivative, two words, the derivative of a quadratic function meaning x squared, that's the highest degree, is always linear. Which means it's going to have an x to the first in it, okay? Now, whatever your quadratic function is, like it could be, just an x squared or an x squared plus 5x minus 7, whatever it is. If you have a quadratic function, when you take its derivative, it will be something linear, okay? All right, last one. Same concept as the previous. We want to figure out which one of these functions is the original function and which one happens to be its derivative. Now I can see it right away, so I'm going to point it out to you, but the green one is going to have to be the original function, and the purple one's going to have to be the derivative. But the easiest thing, I think, to see it is those turning points. So, for example, the purple one has just one turning point, which means if the purple one was our original function with one turning point, the green one would have to be the derivative. It could only touch the x-axis one time. That's the only place on the purple that has a zero slope, but that green one doesn't touch the x-axis one time. It touches the x-axis 3 times, so that can't be the direction. That means, again, that the green one has to be the original function, and the purple one has to be the derivative. Okay, so if we look at f of x as the original, okay, again, I have a zero slope here, right? Zero slope here, turning point, zero slope here, turning point. At those two zero slope places, at those two turning points, my original function should touch the x-axis, which I do, or which it does, right here and right here. So m equals 0 means x-intercept here. M equals 0 means x-intercept here. And then just like the last one, all the increasing and decreasing corresponding with positive negatives, that happens. Just it turns into a big mess. So I want to show it to you, but maybe don't write all this down. But just so you can see it. Okay. So on our original function, before this first turning point, my graph is increasing, which means the corresponding graph there on the derivative function should be positive, which it is. This is the corresponding piece of graph. The same interval, this corresponding piece, again positive, above the x-axis. And then after the turning point here, this is decreasing. And so the corresponding graph on the derivative function should be below, it should be negative. It should be below the x-axis, which it is. And then finally, after this turning point, f of x is increasing, which means here we should be positive or above the x-axis, and it is. So if you look at the corresponding domains, again, where f of x is increasing, f prime of x is above the x-axis. where f of x is decreasing, f prime of x is below the x-axis. And that's positive and negative, corresponding with above and below. But I think the zero slopes are probably the easiest giveaways. Hopefully it makes a little bit of sense. And again, you're not going to be asked to draw any of this on your homework, and this isn't a huge focal point of what we're doing. So do your best with the assignment, and if you need some extra help or clarification, then just reach out. All right, so for now, until next time, take care.